Yeah, thank you for coming back. Yeah, this is the second talk I'll be giving, and it's very different from the first one. So the first one I thought of like, more like an introductory, like, more colloquium style talk with some technicalities later on, but like, a little bit of an overview. In the second talk, I want to talk about what I really like technically. And you'll see that while I'm not the person in my mind, I'm just old, which means I don't actually program a lot of neural networks, actually, no. I really like, I'm in love with the details. And I'm especially in love with Bayesian networks because they are, if you think about it, the kind of networks that we would write if physicists or particle physicists, like, were to, like, invent a network. Luckily, they have been invented before, so we don't need to invent them. So I'll briefly give you an introduction to Bayesian networks today. And that is starting from the general statement that, as we learned last time, and as you know, and you played with them and like did your projects, neural networks are nothing but just functions, right? I mean, they're just a function of phase space and give you a number of some kind. And that's the same if it's a regression network or classification network or generative networks. These are all always like, numerically evaluated functions. And they're constructed for minimizing a loss function that we also know. And if you think about it as a physicist, like, after like, your like, first year or like, undergrad, like, classes, or like lab courses, that this is just like a minuet fit or whatever you use nowadays, like, in Python tools for a fit. And you also know that when you do a fit, every fit result comes with an uncertainty, like, you fit a function and then you sample the fit parameters, so the parameters in your fitted expression, and then you sample those. Wait, I need to close my door here. I apologize, that was the hospital helicopters. So we fit a function, and then we get an uncertainty. And the immediate question is, if we can do that for fits, why can we not do that for neural networks? And one thing that is actually I think, very ironic is that we physicists always look down on other fields because we think we're so much better at uncertainty and so on and so forth. I actually heard about and learned about, like, Bayesian networks and uncertainties in neural networks from a medical research group. And so this is like, Christian Leivich's group in Tübingen. I read this paper and I said, I want to try these networks. So like, this is how I came across these Bayesian networks. But let me give you like a little bit of an introduction what these networks do and why they are so attractive. So as you might have noticed by now, I like reading papers and to try, like, to understand where things come from and what we can do with them. So let me start very historic. And that is with a thesis that was written at Caltech in 1991, and that is a thesis by David McKay. And he actually is, I think, the person who, like, if you want, invented structurally Bayesian neural networks. So what he was trying to do is he was trying to, like, use like Bayes' theorem, like, just like, and then encode a posterior, or no, encode the probability, like, an inference probability of a model to being true into a neural network. So he was trying to construct a weight distribution P of W given the data in the model. And the technical things that, like, he had to deal with at the time, or the conceptual things, like, are really not very related to what we're doing nowadays with Bayesian networks, as you see in a second. But he really wrote down, like, the architecture, the whole idea that, you see, this is a probability distribution of weights given whatever input you have. And this is going to come back. So he is the first person, I think, to actually look at these probability distributions and see what can I do with the probability distribution of a weight. Remember, when we train modern deep networks, we don't care. Probability distribution of a weight is a data distribution. It's either weight whatever omega W0 or nothing, right? I mean, like, we don't actually consider these as probability distributions, but we should. Here you see, like, one of the things that he actually solved that here is that, like, how you can, like, learn these kind of weights through backpropagation. So, like, a lot of the things that we think about nowadays are actually readily available from this thesis. right? Now, if you think about 1991, that was actually before what we call the revolution of deep learning, or making networks deep and complicated. So I think that there's some credit goes to Radford Neal in 1995 at Toronto, who basically made these these Bayesian networks. He took them and made brought them into the deep learning era. Deep learning means many layers, complex functions, using also the computational power that was developing, since the 90s. What he did is actually something that we don't do anymore nowadays. What he did, what he focused on it, is about, if our network weights have, some kind of distributions, and I consider this weight space as, a space of representation space, how do I, sample in this space? And so, he focused a lot on this the sampling, which I think what I think is funny here, that one of the concepts he's using there is hybrid Monte Carlo, which again we know is a physics concept. Hybrid Monte Carlo or Hamilton Monte Carlo is a tool that I think physicists developed for lattice gauge theory, right? So this is all very close to our thinking. It's distributions, probability distribution for weights. It's Monte Carlo sampling. And how do we deal with this? I mean, you can read these theses and they're very readable to physicists, right? Even though this is, strictly speaking, computer science. And as so often, I think it's fair to say that, at least the way I think of Bayesian networks, that I like Bayesian networks, goes back to one person, and that's Jaren Gal. That's a PhD in Cambridge, where he said, these Bayesian networks, while they were developed for inference to compute, look at the weight distributions and try to infer something about models, comparison to data, what they actually nowadays much more useful for is for uncertainty treatment, namely saying, well, going back, we have a probability distribution for weight. We know this. This is from a fit, right? A fit value has a distribution, right? I mean, it has a posterior distribution. So let me understand those distributions for individual network weights as a description of the uncertainty in predicting a function, which means I have two things I need to do. I have to first learn a probability distribution, define and learn a probability distribution for the network weights, and then I have to somehow evaluate, sample it. Right. By the way, Jaren's thesis is also a masterpiece in uncertainties and uncertainty quantification basics for modern neural networks. One thing here is, and that's I think amusing. You'll see later that we will make an approximation, and that is about using independent Gaussians for the different weights. Why do we do this? Oh, well, it's because it's simple. A lot of people criticize us for it, everybody nowadays criticized us for and said, this is not appropriate, not sufficient, blah, 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 lots of criticism. This is already discussed in Jaren's thesis. This is discussed in the thesis 7 years ago, where he says, well, if you think about deep networks, the assumptions that you make about your network weight distributions, just like the assumptions that you make about your activation functions, right, are really very far removed from the expressivity of your network. The same way that we are allowed to make an approximation ReLU or whatever ReLU-like nonlinear function for the activation function without actually having huge impact on the expressivity of a deep network, the same way we can use independent Gaussians, which are super fast to sample, to express the uncertainties. And we will have to check this, but I just want to advertise, this is already described in Jaren's thesis. By the way, as I said, he's a superstar. It's really amazing what in this thesis, what he developed as one student. If you want to learn a little bit more about these things, a little bit more formal, a little bit more careful and a little more mathematical, I can advertise Manuel Hausmann's thesis. That's the fourth thesis that for me forms this field. Manuel he did a PhD in Heidelberg, and they're very good friends. And he taught me everything I know about Bayesian networks, because at some point I noticed when I read Jaren Gal's work that there was a guy in Heidelberg who actually he knew huge amounts about it, and so we had coffee and stuff, right? So yeah, so read Manuel's thesis. All of these theses are obviously public these days. So this is a brief story. Important message though, like the reason why do I talk about their PhD thesis, because I'm talking to young scientists, right? And I think these theses are a nice example for the impact you can have if you work on the right thesis topic at the right time and your results are sufficiently great, right? I mean, like, you know, this is young people, like, you know, 4 young people shaped this field if you think about it. And then lots of us followed. And I apologize to everybody who's like listening and like, you know, feels missed out. And I apologize because I might well be missing contributions here. But this is the 4th thesis I read about it. So let me explain Bayesian networks in some detail because I think they're so cool, using a very simple example. And that is, let's use a network to extract the energy of a parton from the jet constituents. So we have jet constituents, lots of them, like, you know, they might have, like, you know, there might be pileup or not pileup, there might be out of cone radiation. So there's also a bunch of physics, there's smearing, there's measurement uncertainties. So there's a lot of, like, you know, physics aspects which, like physics effects which affect the translation of the parton energy to the energy of the sum of all constituents. I mean, it should be approximately very proportional, but like, you know, we want to learn that function, right? You can think of it as an energy calibration if you want. And then I want this function to come with an uncertainty. And from the Bayesian networks, we already know, because they work like fits, the networks work like fits. I want to extract that uncertainty from the uncertainty of my fit parameters, and my fit parameters are thetas, are the network base. Yeah, so that's what I want to do. So let's take a step back, because I think this is a beautiful example to introduce neural networks and how they work and how the training works. So let's start first, like, you know, what I want to extract. What I want to extract is the energy of a jet. And, you know, really what I want to extract, because, you know, there is like stochasticity, like all kinds of effects. Detector effects are stochastic, while they're not deterministic. What I really want to extract is the expectation value of an energy given the probability distribution of the energy that I somehow know from the neural network. So the expectation value of my energy here is the integral over the energy times this probability distribution, right? Okay, and then I want my my energy distribution, P of E, to be described by a neural network. And how do I do that? Well, I describe my my distribution of the energy as a distribution energy given my network parameters times the probability of the net parameters, going back to the Neil thesis, right? If my theta representation is a complete representation, that integral is clearly correct. Right? That just means I'm representing P of E in theta space, right? And these theta distributions are, like, you know, really the distributions that define our network rates. So theta space is big. Okay, so what do I do with that? I just, like, you know, copy this here. So, like, you know, these are just these two, the formulas. Copy P of E is here. The theta P of E given P of E given theta times P of theta given the training data. If you think formally in terms of like what people call the variational approximation about what network training then means, is that I replace the probability distribution given the theta and given the training data by a universal learned distribution Q of theta, where training data is kind of taken care of. It's trained, right? This approximation sign here says network training. So I have a probability distribution for the thetas given the training data that I want to describe, and, like, you know, I don't want to rely on the training data, right? I mean, I want a universal function encoded in the network, and that's Q of theta. If you look at this equation here on the left and right hand side around this approximate sign, you see what I want then is, mathematically, I want to train my network to express Q of theta such that it, under the integral, its shape replaces my P of theta given the training data. P of theta given the training data is what's encoded in the training data, what I can extract from the training data. So one way to do that, and I'm sure you have heard about this by now, is to look at the difference of those two distributions in terms of a divergence, or specifically the KL divergence. Why the KL divergence? In some way, because it's the simplest distribution you can choose. You can choose others, but the KL divergence, as you will see in a second, is just the simplest and fastest. And it's sufficient, right? There's this whole field of optimal transport, where that thinks about other alternatives, but KL is found for us. So you write down the KL divergence. That's just the definition here on the right-hand side. Theta integral Q of theta sampling log Q of theta divided by P of theta. If the two of them are the same, under the log, the function is always 1. That means the log of that function is always 0, and then it's sampled over Q of theta, it's still 0, right? If it's not, well, then it's some kind of value. Okay, now the problem with Q of theta given T, the weight distribution given the training data, is that I can't express it. I don't know what to do. However, I know that the other way around, P of the data training that I'm training given theta, this is something I can generate. This is something I can evaluate. So let's use Bayes' theorem. And this is, by the way, why these things are called Bayesian networks. Use Bayes' theorem to translate that distribution P of theta given T into a likelihood P of T given theta, and then times the two correction factors, the prior P of theta and the evidence P of T. Okay, and then all I do is I split this log into 3 different terms. The first term I get is the KL divergence of Q and P. So the distribution Q and the prior P. We'll see in a minute what that means. The second term is minus the samples, so d theta Q of theta, log of the likelihood, log P of T given theta, right? And the third term is log P of T, this is the evidence, times d theta Q of theta. Now, if you, by construction, manage to ensure that your Q of theta, your distribution, your Gaussian of the weight distribution, is properly normalized, then that becomes log P of T. There's no theta dependence, which means we can drop it out of the training. There's actually a cute little mathematics background, and that is if you take that log P of T and you solve for it, you get these other 3 terms. You know that the 1 KL divergence, the first one in this expression B of Q and P, and the likelihood is always larger than 0. So you get an inequality. This is called the evidence lower bound, elbow. All that means for us is log P of T is well-defined. It's a well-defined number, you can compute it, and it's not part of our training. So that means if I want to minimize the KL divergence that in the upper formula here describes the training of P of theta given T being approximated by Q of theta, then my loss here, as you see here in the bottom, has 2 terms. It has a negative, it has a negative log likelihood term. Remember, losses are minimized. A likelihood to agree with data you want maximized. The log just change the scaling, right? So this is a sampled negative log likelihood that my networks theta parameters reproduce the training data. So that we understand. This is a likelihood loss. We'll see in a second. Plus a KL divergence Q of theta, P of theta. That somehow you choose a prior, some kind of shape of P of theta, and then your Q of theta should be similar to that. This plays a very specific role. You'll see this in a second, right? Actually, you all have seen this kind of term in your lives, and it's very simple. Let's write to understand it a little bit better, and because we'll do it anyhow. Let's assume that I want my Q of theta, my probability distribution of the network parameters, I want them to be Gaussian. Why? Because Gaussian is compact in the middle, tails exponentially suppressed, easy to sample. Simple thing, right? So standard, some Gaussian described by 2 parameters, the mean and the width. And let me assume that my prior distribution that I want to approach, P of theta, I just choose that to be a Gaussian as well, so to make it consistent, so that the whole thing can actually converge on something. Now, you're lucky, or we are lucky when we do that, because the KL divergence of 2 Gaussians we can actually write analytically, and you see the form here. It's a form of sigma Q, sigma P, mu Q, mu P. So these are the mean and the standard deviation of my prior distribution, so my boundary condition, and my actual distribution is Q. Now, look at this above curve, the formula here. And now let's think, what happens if I have a non-Bayesian network, a deterministic network? A deterministic network is a network where all my weight distributions shrink to data distribution. So like, my weight has just one value that's called, that we call this theta 0. Now, when you evaluate this formula here and the limit of vanishing sigma q, right? And then you can and then you look at mu, and mu is mu q here is theta 0. That's just my one value that's allowed. Then this form above here breaks into, okay, sigma q vanishes over sigma p. Sigma p squared divided by sigma p squared is just a number. It's 1/2, right? Like minus 1/2. So it doesn't matter, constant. What we care about is this squared term, and that is just I copied over. The same thing I can do for the likelihood term here. Q just because it becomes a data distribution. That's my loss. Now, look at this loss. And you all have seen losses now. So what's that loss? Well, this is the standard loss of a likelihood loss of a network. It's like the first one is a likelihood loss. You can make that Gaussian if you want, right? Then you get the MSE. And the second term is, upon closer inspection, an L2 regularization of the network weights. So, what we have just learned is a Bayesian network has an automatic L2 regularization with a prefactor that is fixed through Bayes' theorem. So the Bayesian network is super stable because it has no regularization included, right? So the way we physicists would write down the network, it's regularized. The other thing is, let's think a little bit about the sampling here, the Q of theta. If you think about the sampling a little more, you can think about, you remember that in classic networks, there is a concept that also avoids overtraining. That's called dropout. Dropout means you either include a weight in your training or you do not, right? If you think about this variational approximation, that's just an extreme case, right? This is just choosing Q to be 0 or 1. Q can have two outputs, 0 and 1, and then the two of them give a mean. Doesn't matter, right? Now, if you replace our Q of theta by a Bernoulli distribution, which can have outputs 0 and 1, and you formally do this, then you get this additional, this term here. There's the minus rho prefactor, which is the expectation value, times the likelihood loss. So what you can also see is that our Bayesian network, this Q function, is a moderate version, less extreme version of the dropout, because dropout is nothing but a Bernoulli distribution in Q. So two things that our Bayesian network does. It has the likelihood loss, and it has built in two things, two ways to avoid overtraining, which are established in machine learning literature: regularization, L2 regularization, and dropout. So that means the way we physicists would always want to write down, following Jaringal, the way we would want to write down a loss function for a neural network has automatically regularization and dropout included. These are not aspects that magically come into constructing a loss function. They also do that, but if you think carefully and you do it right, they actually come out of the derivation of the loss function. They are not extras that go in, right? They don't have to be added; they're in there if you do it right. So if you take a Bayesian network, you go into the limit of deterministic networks that come out. So that's beautiful, I think, because it shows us how to construct a loss function properly. Notice that here I also include a likelihood, and that doesn't have to be the Bayesian, the Gaussian approximation. It could, but it doesn't have to, right? And you remember the MSE is just yet a rougher approximation to that. It's a mean field version of the Gaussian approximation. Okay, now I need to evaluate that network. I have coded, I have coded it, I have trained it, I have it. Q of theta it's called, right? And now I evaluate it. So I go back to my formula here. This is my original formula. Nothing has changed, right? Here is P of E. This is all just included here. So E expectation value, an E integral, a theta integral, and then the different P's. I just copied that here. The way you evaluate the network is you switch the two integrals, E and theta. So you first form a theta dependent average value E here, or expectation value here, E bar, right? That's just defined like this, which is E of theta, E bar of theta, right? It's the expectation value E given a theta reference, and then theta. And theta is the stuff that I'm then sampled from. So like theta will be numerical, right? The nice thing about this is if you look here, E bar, well, if you know how to calculate this E bar here as an integral over theta, so that's an expectation value, you naturally know how to compute a variance of that, like, the usual way. So like, now you take, instead of dE d theta here, dE d theta, instead of E, you put in E minus E expectation value whole thing squared times the same two terms, P of E given theta, Q of theta, right? So I know how to do this. And here comes a little bit of a mathematical trick. So you can, like, form the square here. And that would be like, just writing it out here. This is, and integrating the E's. So it's the theta Q of theta, and it's E squared bar minus 2 E expectation value E bar plus E expectation value squared. That's just like, multiplying it out. And then you play one trick. You introduce a minus E bar squared, and you, like, at the end of the day, you add it back. In that case, you get two contributions to the variance. The first one is a sampled version of E squared bar minus E bar squared. We know that is a typical form of the variance. Tells you something about E distribution, P of E. And the second term is something that's E bar minus E expectation value whole thing squared. Now, let's think about these two terms for 1 second. What happens to those? When are they small? When are they big? Now, look at the second term first. This is E bar minus E expectation value whole thing squared, right? So when does this vanish? Like, when is this small? So like, what does that describe? Now, go into our network approximation for the where the Q's are all theta, deltas, which is our deterministic network. You see, just from the definition, right, that in that case, E expectation value up here is nothing but d theta, that is E bar. E expectation value is E bar. E expectation value here is E bar. This whole thing is 0. Multiplied by the delta distribution, integral becomes trivial. So that's clearly 0, right? So we have one term here, the second term to be precise, that describes the quality of my network training, the distribution, the width of the theta distributions. That means if my theta distributions are super well trained, they're very narrow, that second term here that forms the uncertainties will go to 0. Now, the slightly more complicated term is the first one here. Now think, this is E bar, E squared bar minus E bar. When does that actually vanish? No, let's look at the definition of E bar, and you see that vanishes if P of E becomes a delta distribution, right? Then E bar squared and E squared bar are the same if the E distribution is a delta. And that means, again, we have a second term, and that vanishes, well, if my energy probability, that has nothing to do with the training, with the network, that's the data, right? If my probability distribution of the energy is actually narrow, right? So when would that not be the case? That would not be the case, for instance, if your data is stochastic. If your energy data is stochastic, then, like, you have like an inherent like distribution here, and that's not 0. And the second thing is that's also not going to vanish if your network, this is E given the training data. If your training data, like, for some reason, like, give you your network parameters, if your network parameters cannot describe that function very well, then you get also a funny distribution, right? In which case, also you get a sizable contribution. So we have two terms. One of them depends on the quality of my network training. The other one depends on the nature of my data. So, and now we can separate them. By the way, if you think about it, the first one in physics language, the first one, if you have, would vanish in the limit of perfect training, which means a nice network architecture and infinite amounts of training data. Then your network will be better and better trained. So you can think of this as a statistical uncertainty, whereas the second one is a more systematic uncertainty, something you cannot actually discuss away. Well, I mean, there's nothing you can do if your data isn't good enough. Okay, so now, if you think about here, these two, actually one of them, predictive uncertainty, you need to extract a sample over theta, to actually get it. The first one here is a well-defined function of theta. So what you do is in your network, you like learn the stochastic, the systematic uncertainty of theta, and then the first one you get from sampling. So your network now predicts in terms of x and theta, actually two functions, E mean S of theta, or expectation value E bar of theta, and sigma stochastic of theta. All right? And now you can write your likelihood again, and this is just the final form here. That's the final form where you write this likelihood as like, a sampling here over Q of theta. And here what I've done is I have just assumed a Gaussian likelihood for my data. So this is E minus E truth absolute value squared divided by 2 sigma. And then log sigma here is the prefactor of the Gaussian likelihood. And the second term here is for 2 Gaussians, the L2 regularization. By the way, side remark, that thing here, this loss is also called the heteroscedastic loss, and you don't have like, I think it's also introduced by Yarengal, but you don't need a Bayesian network to use that loss. If you want a network that to learn an uncertainty together with a central value, then you can just use that loss. What does that loss do here? It's actually not that hard to understand. Sigma is something the network learns. It's a function of the same space that your energy lives in, of phase space, right? So sigma you learn. So what can you do, like, to learn it? Well, in the first term, the network can either model the energy extremely well so that the numerator becomes small, or it can make in case it cannot make the numerator small because it's lacking expressivity or whatever, it can make the denominator large, right? So the first term will become small either like, the network is very good, so the numerator vanishes, or the denominator gets very big. However, because of the prefactor of the Gaussian, there's a second term log sigma stoch, which penalizes the second solution. So the network will not like, if it has a choice to increase the denominator, it'll prefer to reduce the numerator. Right? So, and this is, if you think about it, exactly what we want. So you want a network that models the function as well as it can. If it cannot actually get better, compensate in the loss by introducing an uncertainty, sigma, but make that uncertainty small as you can. At some point, it's the smallest you can do, and then that's it. That is the uncertainty. Yeah. Yeah. And what does this uncertainty encode? Well, as I said, predictive uncertainty is training statistic. Stochastic uncertainty, systematic uncertainty from data, label augmentations, model limitations, all the other thing are the systematic part. Maybe I should call this in the future systematic. Okay, and that means we now have a network that gives us, in addition to the expectation value E, the output, it gives us 2 uncertainties, and they're adding quadrature. So, old paper, when we first came up with this, let's test that. Let's see what it does. And the simplest example is exactly what I just show you. It's measure the transverse momentum of a top that decays hadronically from a top jet. All right. So here you see, on the right-hand side, with and without initial state radiation, you see that for a jet PT, so the top jet PT of anything between 600 and 620 GeV, the underlying truth distribution for the top, right, has a certain width. And you see this has a width of about 50 GeV upwards, up and down, right? So it's not that narrow. And yes, that distribution depends if you include ISR or not. Why? Well, because without ISR, without initial state radiation, a jet can really just lose energy. It can't gain energy, but there's nothing to gain from. Which means without ISR, the truth PT of the top will almost always be larger than the PT of the jet. So you see that you have this thing move to the right. With ISR, it's different. ISR can just put stuff into your jet, extra jet activity goes into your jet, so it becomes more symmetric. I'm more interested in without ISR because I want to see how a Bayesian network deals with non-Gaussians, with non-Gaussian distributions here, and that's the orange one. But before we do that, let's look at the 2 uncertainties, the training size, sigma predictive, and the systematic or stochastic uncertainty, sigma stoch. Remember, in quadrature, they add to the full uncertainty. Now, what we did here in the old days is we looked at the uncertainties as a function of the training size of size of the training sample. And you see that the two uncertainties that we have, the blue one, the predictive uncertainty, and here the complete or the stochastic uncertainty, they behave in a very peculiar way. The blue one, the predictive uncertainty, goes to 0, comes down here. The combination of them comes down here, and the dotted line here, the orange line here, the stochastic uncertainty is almost flat, which means our uncertainty indeed describes a statistical and a systematic aspect. If you want to check this, by the way, you can do the same thing with the frequentist dropout network, and then ensembling, and you see a very similar behavior, similar uncertainty. So this is all fine. You can reproduce the Bayesian network uncertainty, albeit in a much less stable version, just ensembling in the network. What we see here, by the way, is you see immediately, right? I mean, there's two different uncertainties. For our application, clearly the stochasticity of the data is much more damaging than the training data, amount of training data. So we have enough training data. That's what you learn from such a study. Don't need more training data. More training data will not help with improving in my network training. Yeah, and we always check with deterministic network and ensembling. Here's something like, can I describe non-Gaussian version? Because we always get criticized, can you do this? Because your theta distributions are Gaussian. Well, we can, because the theta distribution is not the uncertainty of my network output. My network output is sigma stock, right, for instance, or sigma pred. And you can easily, trivially replace the stochastic uncertainty that we had here. You can trivially replace this by a Gaussian mixture model if you don't want this to be Gaussian. So we don't want a likelihood to Gaussian or Gaussian mixture. And then you see that this is exactly the Gaussians that you see that we need to model this orange curve that is what we want, the truth here. We have 3 blue lines. The first one Gaussian peak, a second Gaussian peak, and a very flat third Gaussian peak. And with 3 Gaussians, we can describe this very non-Gaussian distributions, no problem. So in other words, the fact that as in this training, the thetas are actually Gaussian has no impact on the the form of the uncertainty that we get out. That's a whole different function, and that we can make non-Gaussian trivially, very easily. Right? So in other words, Jaren Gall, as expectedly, was right when he said you can use Gaussians for thetas because a deep network can model very non-Gaussian uncertainties, even if the individual building block is Gaussian, because it's a deep network. Okay, let's skip that part. Now, let's apply this, not to energy. Let's apply this to something else. A very typical theoretical physics problem: in amplitude, glue to gamma glue, or to gamma glue. This is an amplitude. It's the same task, right? We want to learn a function in amplitude as a function of phase space. The reason why I chose this one here is because I'm a theorist and I know that if I train such a network over my phase space, right, and it is not precise, and precise means it does not get these amplitudes right at the whatever % level or better, then my friends in Durham, Karlsruhe, Zurich will look at it, shake their heads and say, well, nice try, but not good enough, right? Loop people have, when it comes to precision, no sense of humor, right? I mean, this is either you deliver your precision or you do not, right? And they want to be sure that you deliver your precision. So now the question is, similar to the energy task, can I actually learn the uncertainty? Would I impress with my Zurich, Karlsruhe, Durham friends by saying, I can not only learn this extremely precisely, I can also give you an uncertainty on A. And this is when they their faces lighten up and they're like, oh no, that would be very nice. Well, especially if you can trust your uncertainty, obviously, right? You have to show that. And if you have the uncertainty, then you can actually look at the output of the network as a function of phase space, and you can even calculate something like a pull, right? A pull defined as network prediction of the amplitude minus the true value of the amplitude in this point divided by the uncertainty in this point, right? And we know how this pull should look, right? I mean, a good pull is pretty much Gaussian. It has tails. Every function has tails, but it's going to be very compact. It's going to be a Gaussian shape. It has a certain width that gives the uncertainty, and it has exponentially suppressed tails. This is when we are happy. right? So here you actually look at, like, see some of those pulls here, like, for this, for these networks, right? The difference between, by the way, here left is linear, right is logarithmic. Linear, you see it looks pretty Gaussian. Logarithmic, you see when you go down to this, say, like, 1% level, my numerical width becomes larger than Gaussian width. But this is, by the way, always like this when you look at, like, simulate stuff. Your tails are always a little bit larger than the suppressed, than the Gaussian tails. Now, we actually played some trick here using this pull, because we thought, okay, if that pull points to regions of phase space which are, like, which populate the tails, maybe we should be able to do the tails better, just as a self-consistency check. I'm not looking at where in phase space I am. I only care about, like, looking at automatically improving my network in regions of phase space where it's not learning well, which means by its own standards, namely by its own sigma, where the pull is large. So in other words, where A bar minus A truth divided by sigma is large, right? And here we played a little trick that everybody can do, and that is like reminiscence of, like, boosting and boosting decision trees. What we basically say, if you take your training data points and you find that this pull here is large, well, give that phase space point more weight. So just, like, add, like, a multiplier here, given that this is a regression task that, like, learns on a predefined value of a set of points, you can do that, right? And then a given phase space point will get more impact onto the loss, and then you learn better. So this is a very practical application of using the Bayesian uncertainty sigma of theta as a way to improve your training. It's very, very practical. Everybody you can just do it. It's very, very simple. Yeah. So we played with this, like, you can push this further and further. Here we can look at the deviation. Let me just, like, show you a little bit more physical observation here. So this is glue to gamma glue process. It's a one loop process that Simon Badger calculated, and this is the eta of the gluon. That's the rapidity of the gluon here, the distribution, and you see that our network that, like, that if we evaluate here on the test data, on the training data, test data is the dashed green and the dashed red line. So this is the data, and the network evaluated on each of these data sets is a solid line in green and in red. And obviously that's almost impossible to read. So, like, the next two, like, lines, subpanels show you the agreement of the model over the training data, right? For test and for training. So for train in red here and for test here, just as a deviation. So I want to know how good I am. This is plus minus 20%. What's interesting here is this precision is then contrasted with the statistical uncertainty on the training data, which is the gray bands. And what you see here is that because of this boosting, our network is so much better than the uncertainties, which means there is a certain amount of overtraining happening. But now you look at the test comparison, so this independent data, and you see that we get a little bit of an uncertainty, a difference between green and red and green here, but the difference between green and red is still better than the statistical uncertainty of the training data, which means our network has learned the stochasticity of the training data correctly, right? So we can really use that to improve our training in a real physics problem. And you see, we're talking a couple of percent. This is, like, what our amplitude friends in, what I said, Karlsruhe, Zurich, Durham tend to want, or better. They want better. We have to work on that. The last thing I want to show you is something that, like, I think in my group, like, that we introduced for the first time, and that is a Bayesian version of generative networks. Normally in machine learning, Bayesian, uncertainties on generative networks are simply not the thing that most people are concerned with, to be fair, right? They don't really care. ChatGPT uncertainties are not the leading question, right? For physics, that's different. Like, almost all our generative networks generate some kind of events, showers, whatever you want, detector signals, I don't know, everything over phase space. So I want to approximate a phase space density through my sampling. And that phase space density in physics tends to be well defined, right? It's like, we know what phase space does and it's already defined. So now the question is, the phase space density that my network has learned and that, like, it generates through sampling, can I compare that to the phase space density of my training data, right? And if yes, what's the uncertainty of estimating this? And this is what we train a Bayesian generative network to do. And I don't want to go into any technical details. You do this the same way you train a regular network. And you can read our lecture notes, our Heidelberg lecture notes on more details of that, right? And what I'm using is normalizing flow here, because why? Because, well, I told you about this last time. Normalizing flows are bijective networks. Bijective networks are super stable, and especially bijective networks, it doesn't matter where in my latent space or my representation space I define, this uncertainty, because I have the Jacobian, and my Jacobian transforms the central value as well as the uncertainty, like, in a well-defined manner between these two spaces. So, like, I'm on very solid ground. Now, here in the upper part, you see the density estimated, like, from sampling for a very simple toy model. My simple toy model is just a ramp in one direction and flat in the other. Why flat in the other? Because a normalizing flow typically wants 2 dimensions because of the standard setup of a coupling layers. So, okay, I have this ramp, and now I can ask, how does the uncertainty look on that density, as that density is estimates? Now, first I check here, is the rough order of magnitude of this uncertainty correct? And you see here, this is, like, the blue band that you can see is the uncertainty on the density, like, that I get. The truth is red, and the blue line is the central network prediction. Here in the top panel, you can hardly distinguish them. So we have, again, the ratio, and you see the ratio of the Bayesian network to truth is pretty close to 1. It gets a little bit worse in this region where you don't have a lot of training data, which is expected, right? The other thing is, you see that the Bayesian uncertainty on this density covers the deviation from 1 pretty well, right? First of all, like, here you see it's actually quantitatively about the right value. And then you see it also gets larger to the left where we have less data, and so the agreement gets worse, and the uncertainty goes up. So that's exactly as expected. Now, what you do is you plot just the uncertainty, just the sigma, right? That we have here, not the central value. You look at the sigma, and the sigma with uncertainty is the blue line here. So this is a sigma evaluated a few times. I wanted to make sure that that curve here, or we wanted, this is Marco Bellagente, we wanted to make sure that this curve here actually is stable. And now you get a funny effect, namely that the uncertainty has a minimum at 0.4 or 0.5, like, somewhere around here. So initially you say, like, how can that be? Like, there is no data to the left. The uncertainty should be large in the left, and the uncertainty should be smaller to the right because there's more data, right? So normally you would expect the uncertainty to just go up like this. Thing is, it doesn't. And why does it not do that? There's 2 ways, alternative ways you can express this. Like, one is very basic, and said, like, well, I have a 2-dimensional space, and clearly if a network is good at learning correlations, there's going to be a sweet spot in the middle where it can actually grasp information from all directions around, and this is going to be where it's going to be most stable. This is a very heuristic explanation, and it's correct, right? Your uncertainty is the best in the middle, where you can exploit the most correlation directions. There's another way of explaining this minimum, and that is more specific. You can say, well, let's do some, like, error propagation. Let's write down the function p of x, which is essentially linear. So assume the network learns something is linear, but it doesn't know, now it have to write this as a density. So, like, this is a density x max, x min. So I'm putting in the normalization condition here. And now I do error propagation. I said, like, the uncertainty on the density value dependent on the estimation of A, the maximum and the minimum here, has, like, these 3 terms. The second and third term is independent of x, so it doesn't matter. Just it's a number, right? Depends on it. However, the first term, the uncertainty on the density that comes from modeling A, so the slope, has a prefactor that vanishes at 1/2. So in other words, if you were to know that your function, the density of a phase space is described by something like a linear function, and now you fit the linear function, you fit the prefactor, you fit the slope, you will also find that this is a minimum. So that means, and we have shown this using other examples, this means that our Bayesian network really just works like a fit, right? It estimates a rough functional form, and then it kind of tunes the parameters. And in this parameter tuning, it sees exactly the patterns that we would see in a fit, which is not very surprising because I introduced them at the whole thing as a fit. Fine, right? So INNs are really just non-parametric fits. Now, something we did more recently, and that's the last kind of set of things I want to show you, something we did more recently is ask the questions, alternative architectures, modern networks, we wrote a paper on that, modern networks which are triple diffusion networks, or transformers, what are those? And we tested this. And now you see exactly the same kind of like plot here. This is just my ramp here, my linear slope. And this is the uncertainty for a discrete diffusion model. For those of you who know it's DDPM model, right? For the DDPM model, you see that the uncertainty sigma here, the absolute uncertainty for that looked so nice here, and when had this distinct minimum, is actually, well, it has some structure, but it's not that anymore, which means there's probably something like a fit going on here. However, the functional form isn't as well defined as it is for the INN, for the normalizing flows. And therefore, this very distinctive structure of a minimum at 0.5 gets washed out. So what it tells us is something that we also know, is that diffusion models are a little bit similar. They work a little similar to normalizing flows. However, their functional form is more flexible, probably. The expressivity is higher. A continuous diffusion model, that we also tried, out, and this is the conditional flow matching for those of you who know more about it, right? Again, we did the same thing, and you see now it becomes even less of a feature, right? It compares flow, DDPM, so this is almost a constant here, right? It's almost just going up. So the CFM model, yeah, it is in many ways very much like a flow. However, the balance between fit-like behavior and higher expressivity and less of an inductive bias is swinging further to the higher expressivity, which, by the way, is how everybody thinks of continuous diffusion models, right? So going from a normalizing flow to discrete to a continuous diffusion model gives you more flexibility in describing your functions. However, it's also in that sense less stable. Less stable, by the way, just means also oftentimes at least it needs more training. By the way, that subtly, I'm showing you that we can make any generative network Bayesian if you want to. The last one I want to show you is the autoregressive transformer. So this is the architecture that's behind JetGPT, just for LHC here, or in our case now for our toy model. And you see that is not a functional estimator, right? I mean, this is really uncertainty just growing with more data. And sigma over p, relative uncertainty, going down over data. So this is much more like if you think a patch-wise estimation. This here is the result for bins. If you replace the density estimation for the transformer with the Gaussian mixture model, you see that it becomes even more extreme. The absolute uncertainty here goes up with higher density. However, the relative uncertainty just comes down like this. I should admit, by the way, this is what I would have expected for the flows originally. We had lots of discussions with my poor student Marco, who had I was a real pain because I wanted to see that curve for the normalizing flows, but it's not right. right? So what we see is that going for normalizing flows, 2 diffusion model, 2 transformers, we see that the way these Bayesian networks behave, and so that means the way that my networks learn the underlying density, that it becomes more and more like, patchwise density estimation as compared to a fit of a functional form, predefined functional form. And by the way, I'm not saying it's better or worse. All of these applications will have their strengths and their limitations eventually. So it just shows how different these models actually work. I already showed you last time the right-hand figure. This is just a reminder from my talk last time. So question: can we use this for LHC physics? And the answer is obviously yes. Any like phase space generator, you can actually do that, and you can estimate the uncertainty like this Bayesian network here. So we're talking about this thing here, the Bayesian network over like in the truth. You see the blue curve here and the green curve. So my density, my training data green. You see my blue, my network prediction here, and this will actually more like a gray here, and then you see uncertainty shaded gray, and you see how that covers the one, right? But we talked about this already. So this is the uncertainty estimation. What I just explained to you is the technique behind this uncertainty estimation, and that's it. Like with that I'm done. So things to remember for Bayesian networks is, well, first they have nothing to do with Bayesian. I mean, they use Bayes' theorem. If we call everything that uses Bayes' theorem Bayesian, then truly there would be only one Bayesian world, because the Bayes' theorem is strictly correct. There's no arguing whether that is correct or not. So Bayesian network, there's nothing Bayesian about them. They were developed for inference, and I don't want to go into the details, but I think generally people have convinced themselves that for inference, one shouldn't use Bayesian networks. There are better networks to use, which are conditional generative networks. However, it allows us to do network regression with error bars, as I showed you. I didn't show you classification, but this is clearly trivially the same as regression. And what I like about it, it also shows us that we can evaluate uncertainties for generative networks, and that's something that we really need in LHC physics. And here again is the linked version of our Heidelberg lecture notes, where there's many more details on that. And with that, I say thank you, and thank you for having me twice, and I hope you are having great fun there.
Thank you very much. Okay, let us have a couple of questions.
Hello. I have one question regarding the probability distribution of the weight function that you showed in the regression method. So P theta, that you assume it to be normal distribution. So how do we enforce that this is normal distribution or some other distribution?
Which one? This one here?
No, before that.
Oh, the E theta. Oh, you mean how do I enforce? Pretty much here. How I enforce the P and the Q to be Gaussian, right?
Yes.
Oh, sorry. Like I wasn't clear about this.
I understand it is approximation that you want to do, but
yes,
P theta that we have to enforce or somehow tell the machine to do it, right?
Yes. So what you do is, it's very simple. You at some point you need a functional form of your distribution Q, right? P is something that you just evaluate, right? You just give it a Gaussian. You basically say network. Whenever in your loss function you need to evaluate P here. Now down here, just like evaluate a standard Gaussian. And by the way, we should vary the width of that standard Gaussian by orders of magnitude to make sure that that prior. I don't think this is a prior. I think of this as a hyperparameter, really, right? To make sure this hyperparameter does not affect the network output. If it does, clearly you need to think about it, right? It's like for any other hyperparameters. So, this you can check and you just put this in. So typically you give it a Gaussian and you it's going to a standard Gaussian, and then you look at what the width of that and see how that changes. Q is the function is how you actually encode this stuff in your network. And you actually, you see, you need this for sampling at the end, right? Do we have it here? Yeah, here, the E bar. You need to sample it here.
Right.
And what you do is you really encode Q as two numbers, the mean and the standard deviation of a Gaussian, and you learn the mean and the standard deviation. So effectively, you learn two values in your network, mu and sigma, for every theta weight, for every weight of your network layer. So what you effectively do is, instead of learning in a regular network a network parameter theta, which you remember can be a weight or a bias, right? These are typical networks, and understand it like feed-forward network. Now you learn for every weight or bias, you learn a central value, a mean, and a sigma. And once you have those, and you assume it's Gaussian, when you sample it, you sample according to the Gaussian shape. Yeah, so what you do is effectively you have two networks. You have the mean network and the sigma network.
Right, right.
Yeah.
Okay. Thanks.
Thank you. Any more questions? More question? I have one question. When you have shown that this without IISER and that thing from that truth level, yeah. So without IISER, so this truth level, this 600 to 620, this peak is a truth level peak. So when you reconstructed with jet, then you got a this distribution, and then you told some bins below that one was not valid for without IISER or something.
Yes. Okay. So what I plot here, you have to be careful. We plotted this a little bit in a backwards way. So what I'm plotting is for a given jet, the truth the truth top that you need to get the jet energy of 600 to 620. So on the x-axis, it's the variable truth, the label, if you want, of your jet, and PT jet is just the PT of the jet that you can measure. And so here in the right-hand tail, you have truth values. So the top has a transverse momentum of 750 GeV or something like that. But the jet always has 600 to 620. That means if your truth was here, you have lost 100 GeV due to probably out of jet radiation, out of cone, right? And so that means your truth has to be larger than the jet measured.
Okay, now I see.
I apologize, the plot is the other way around from what we normally think.
Yes. One more question.
Thank you, Tilman, for this talk. I think this is the only one major talk we had on the Bayesian networks. Just a general curiosity, where do you see, so there are many other generative networks, but where do you see a promise of Bayesian network over the other network tools that we learned in these days?
Yeah, I mean, first of all, I don't think Bayesian and non-Bayesian, I mean, you can, so almost any network that you like, that has something like a likelihood loss, you can turn into a Bayesian network, right? Any network that, if you think about it, has a loss that looks like a big, do I have it? Anything that looks like a likelihood loss, you can turn into a Bayesian network, right? By introducing the KL divergence here as an L2 regularization, and by then introducing, right, the sampling term here. But it has to be a likelihood loss, I believe. Otherwise, it's tough. In my experience, two things. First of all, Bayesian networks for relatively simple tasks, like regression tasks, for instance, they have two great advantages. First of all, they are automatically protected from overfitting or overtraining through the dropout and the L2 regularization that's built in. So it turns out they're very stable. I mean, if you train them, they're very stable. And the second thing is it gets to an error bar. So if you want something where you need to be precise, right, and control the uncertainty, I would always use a Bayesian network. I should say, by the way, Bayesian networks are not that much slower to train than other networks. We're talking factor 2. So Bayesian networks are at most a factor 2 more to take more factor 2 more time to train. Like ensembling networks, well, you need to probably evaluate, I don't know, maybe 20, let's say 20 networks to get some kind of a distribution. So this is a factor 20. A factor 20 I would hardly be willing to spend, but a factor 2 I can afford. So if I want control, something like and I want precision, I would always recommend using a Bayesian network because it's not that expensive, it's easy to do, and it's extremely useful and reliable. Examples for this is an amplitude regression, like I just showed you. I would always use a Bayesian network because I want to go to my friend Gudrun Heinrich in Karlsruhe, and I want to convince her. And I will say I can control this network. It's well trained, and I have an uncertainty. And I know Gudrun, but the first thing she will ask me is, what about the uncertainty? Right. So that's the first thing. Another thing is what we're just working on is jet calibration in Atlas. The jet calibration people, I know, jet calibration are the people who calibrate jets, which the energy extraction. If you think about this, no Atlas analysis can be done without jet calibration. Or in other words, if you screw up in a jet calibration, you have screwed up every single Atlas analysis, right? It's a disaster for Atlas. So again, this is a set of people who are extremely cool, but they have absolutely no sense of humor when it comes to performance, right? They cannot afford a sense of humor when it comes to performance. If you want to have networks in that, make them Bayesian. You can control them, you know the uncertainty, you know exactly what's happening. So whenever high stakes are there, use a Bayesian network. Another thing, if you don't know how stable your network is, if you want just starting to play with your network, you might want to know where your network is not learning very well, right? I mean, you're unsure, again, Bayesian network, use a Bayesian network because it tells you where the uncertainty is large. If there's enough training data, if you're unsure, use a Bayesian network. So in other words, what you typically do with students in Heidelberg, we ask them to set up a network, they set up a network, something comes out. Next step is make it Bayesian because we want to understand how can we make the network better, what are the limitations, where are we stuck? Again, very typical thing. Bayesian network layers translating in PyTorch or in TensorFlow are very, very easy. And that also applies to generative networks then. Pick your generative network, make it Bayesian so we understand where in phase space, for instance, you're limited by training data. It's when you learn stuff over phase space, oftentimes you get some feature wrong, right? And you wonder, why the hell do I get that feature wrong? What's wrong with my network? First question you can ask, maybe it's not the network, maybe it's the training data, because if it's the training data, you can work on your network as much as you want. You're not going to win this one, right? So here I would say okay, same thing, go for Bayesian network, see, and rule out that you have a problem with the data. And only once you've ruled out that you have a problem with the data, you know that you can improve your network by looking at the architecture. So again, it's it's super useful. I mean, we do it all the time. It's extremely useful to in everyday life to understand what things are going. And we can Bayesianize, as you see here. We have Bayesianized the flow. We have not managed to Bayesianize again in a well-defined manner, by the way, but we can Bayesianize a flow, diffusion models, and transformers, all the same thing. Because all of these networks have at least approximately something that reminds me of a likelihood loss.
Thank you, Tilman. Okay, so I don't see any more question. Thank you very much for your extended talk.